Looks like it is. Yeah, it is. Let's change our ink pen to green. All right, we're in chapter 2, page 60. And we're going to look at number 14. All right, number 14 says we have a race car that starts from rest and travels east along a straight and level track. Okay, so you always draw the problem. So you have a race car, and it's traveling east. And for the first 5 seconds, it tells us that the velocity in the x direction with respect to time is equal to that the component of the car's velocity is given by 0.860 meters per second cubed t squared. Now that's during that time interval, which is a 5-second time interval. Okay, what is the acceleration of the car when the velocity is 12 meters per second? So we want to know what the acceleration is when the velocity in the x direction is 12.0 meters per second. Okay, so that's what we're trying to find, is acceleration when the velocity is 12.0 meters per second. And by the way, it is during that 5-second time interval. Do you understand that this function is only good for the first 5 seconds? So what does this 12 seconds mean? That means that somewhere during this time interval, the velocity is 12.0 meters per second. Now, something else, too, that it said the car starts from rest. So that means that the initial velocity of the car in the x direction is 0 meters per second, okay? So when you look at it, and notice how I wrote these things down. So as you read these problems, you need to write down the variables that you are given. It tells you it starts from rest. Well, that also tells us that x is also initially at 0 meters. If you wanted to write that down, the initial velocity is 0 meters per second, because it starts from rest. And if you start from rest and at time 0, then you have to have a displacement, in this case, of x. Even though it doesn't tell us it starts at the origin, we're going to assume that. Okay? So this number right here is really the final velocity during that 5-second time interval. That's really how you could look at it. You said, well, Mr. Shields, time is in my equation. I do not have a time interval. You are exactly right. You don't, but we can find one. Because look, guys, this function is the same as saying v final, vx and vx final. It would have to be, because we know the initial 0 because it starts at rest. So during that time interval, we know what its final velocity is. So now we can just solve for t. So if we solve for t using algebra, we say our final x velocity, final x velocity divided by 0.860 meters per second cubed. And since that's t squared, we take the square root of both sides, which it becomes t, and then you put the radical on the right-hand side, and now you just plug everything in. So you've got everything under a radical, and that's 12.0 meters per second divided by 0.860 meters per second cubed. Now look, do the math. You cancel that out here, and this becomes squared, and the meters cancel out. And so all you're left with is squared seconds, and when you take the square root of that, you get seconds, because second squared square rooted is seconds, and you get an answer of 3.73 seconds. That should be what you get for an answer, okay? Now we know our time interval. Notice it's less than 5 seconds. So how do we know that's correct? Well, because it's less than 5 seconds. Our function and our final velocity is for that 5-second time interval only. And we know we're right because our time interval is less than 5 seconds. So now we can just take the first order derivative from velocity Remember, first order from velocity is acceleration. Second order from displacement is acceleration. But we're not starting with displacement. We're starting with the velocity. So we say acceleration with respect to time is equal to, well, it's 2 times 0.860 meters per second cubed times t. Now we're just left with t. Now we just come in here and plug everything in, and we plug in our time interval. So the acceleration at 3.73 seconds is equal to 2 times 0.860 meters per second cubed times 3.73 seconds. And we get an answer of 6.4. Watch this now, 6.40, 3 sig figs, meters per second squared. Now, how do you know it's meters per second squared? Well, watch. The seconds cancels this cubed to squared, and you're left with meters per second squared. Okay. Now, let me ask you this. Is the acceleration constant, or is it not constant? Well, look at your function. When you take that first order derivative from velocity and come up with acceleration, notice that there's still a t left in the equation. So that tells me that the acceleration is time dependent. Therefore, the acceleration is not constant because there's still a t in my function, in my equation, okay? Had there not been a t there, then we would have known it was constant, okay? All right, I hope that helps. Now let's go to a clean slide. And let's look at problem number 30. I think that's on page 61. It is. So we're on page 61, if I could write. And let's look at this problem. Now, we have a small block has a constant acceleration as it slides down a frictionless incline. So let's draw our problem. You always draw it first. Let's draw our problem. And let's do, let's fill everything in. So you always need to write that it's friction, I can't even spell. Let me erase, start over. All right, frictionless incline. It tells us that the acceleration is constant, so you need to write all that down. Acceleration is constant. And it says that the box slides down and the block is released from rest, okay? So we got a block sitting here and it's sliding this way and it is released from rest. So if it's released from rest, we know that the initial velocity in the x direction is going to be 0 meters per second. You say, well, now how do you know it's in the x direction, it's on the incline? Because it's oriented to the direction of motion. I know the incline is tilted, but you've got to understand that the block is sliding down this incline, so in a sense that's in the x direction because it's sliding in the direction, it's sliding down the incline, okay? It's not sliding, I know it's elevated to the ground, and we'll get to that later when we get into chapter 5, but again, the surface of the incline is like the x direction, okay? Okay, even though it's tilted. And if you wanted to, you could also say that x initial is 0 meters because it starts from rest. It didn't tell us it started from the origin, but in a sense it would have to say it starts at the top. Well, it said it started at the top, so at the top would have to be 0 since that's the beginning point. And then it slides down, and its speed after it has traveled 6.8 meters to the bottom is 3.8 meters per second. So from here to here, so if x is 0, then that means x final is 6.80 meters. And so that means that delta x is equal to 6.80 meters. You say, I have to get delta x, final minus initial, 6.8 minus 0 is 6.8. And so by the time it gets to the bottom, the final velocity is 3.80 meters per second. I believe that's what it said. So when it gets to the bottom of the incline, it is 3.80 meters per second. Then it says, what is the speed of the block when it is at 3.4 meters from the top of the incline? So we want to know when it's halfway down, so x final here from there to there would be 3.40 meters. So we want to know what the final velocity is at that point. Okay. Well, how in the world are we going to find that? Well, let's see. We don't have acceleration. It says it's constant, but we don't know what it is, do we? It is constant, but we don't know what it is. But we do have a final velocity. We have an initial velocity. Notice this. We have a displacement right there. We have delta x, 6.8 meters. Since it is constant, we can go to our kinematics, and we can look at our kinematics and say, gee, which one of those would it fit? Well, it would fit this one right here. V final in the Vx final would be equal to Vx initial plus 2a delta x. That is the, and by the way, this is Vx final squared, Vx initial squared, plus 2a delta x would be the equation that this would work or fit. You say, well, how do you know it would fit? Well, guys, look at your variables, okay? Look at the variables that you are given. You are given your total acceleration is constant, but you don't know it. You're given the change in displacement. You're given the final initial velocities. So all we got to do now is find the acceleration. You say, yeah, but we're looking for final. I understand that, but since the acceleration is constant, you say, yeah, but that's halfway down. It doesn't matter. Whatever the acceleration is here, it's going to be the acceleration here because it's constant. So we can use the final velocity. Yeah, but that was at 6.8 meters final velocity. It doesn't matter. We can still find the acceleration because it's constant. Okay. And so let's solve this equation for acceleration. So acceleration is equal to Vx final minus V. Okay, let's do this again. I have to be careful. I don't want to erase what I've done. So we solve for acceleration, so it'd be Vx final squared minus V squared x initial divided by, and that's 2a delta x, so that would be what? 2 delta x, would it not? So let's plug everything in. So the acceleration is equal to, the final velocity was what, 3.8 meters per second? Yeah. So it's squared 3.80 meters per second squared minus 0 meters per second squared over 2 times 6.8 meters, 0 meters, yeah. And that's going to give you an acceleration of, where's that? 1.06, and it is 3 sig figs, 1.06 meters per second squared. Okay, now we have an acceleration. So I want to find what the velocity is at 3.4 meters per second. Well, we know at the top it's 0, so now this becomes my new final velocity, okay, because in a sense, you say, well, you already had one final velocity. Yeah, but that was at 6.8 meters. Now we're looking at 3.4 meters. Now we're looking for a new final velocity. And by the way, we can use the same equation, so Vx final squared is equal to Vx initial squared plus 2a delta x. And we know all of our variables. We can find final. So V final, let's finish our equation, x final is equal to, well, look, guys, we know that's 0, but I'm going to go ahead and do this. So it's going to be the square root of Vx initial squared plus 2a delta x. And so now let's plug everything in. Well, x initial is 0, so we have the square root of, so that's what? That is 0 meters per second squared, which is 0, plus 2 times acceleration 1.06 meters per second squared times delta x, which is 3.40 meters. Okay, you say, how do you know? Well, because it asks what is the final velocity at 3.40 meters. And we get a final velocity in the x direction of 2.68 meters per second. So it's 2.68 meters per second. And I want to double check my math there. Yeah, it should be right. Yeah, double check 2 times. Yeah, 2.68. Yep, that's correct. Okay, so that's number 30. So I hope that helps, okay? Do you see that? That wasn't that bad, but you just got to work through them, be methodical, write everything down first, draw it, label it, and write all of your known values down. We knew acceleration was constant. We knew the initial velocity was 0. We knew the initial displacement was 0. We knew the final velocity was 3.8 meters per second, and that was at 6.8 meters. And since the acceleration is constant, it's going to be the same all the way down the incline. So that means we can find it. We can find the final velocity at any point along that displacement at 1 meter, 2 meter, 3.4 meter, 3.78 meters, whatever, okay? Because we found the acceleration. All right, so that makes it a lot easier to work. Now let's look at problem number 32. Problem number 32, and that's on page 61. All right, and this will be our last problem for chapter 2. That I'm going to work, and it says we have a small block is thrown vertically upward with a speed of 22 meters per second from the edge of a roof of a 30-meter tall building. All right, well, again, let's draw it. So we got a building here, okay, and the building, which is in the y direction, y is equal to 30 meters, okay. We can label it that way, 30 meters. 30 meters, and it says it is thrown vertically upward with a speed of 22 meters per second from the edge of the building. So we're right here, and we're going to throw it up, and that velocity is 22.0 meters per second. Now that velocity has to be in the y direction, correct? Well, it has to be because it's vertically, okay? So it's thrown upwards, and by the way, that's and there's the rock, okay? It's thrown upwards with initial velocity of 22 meters per second. So that would be Vy initial, okay? Velocity. Okay? Now, the rock doesn't hit the building on its way back down and lands on the street below. Ignore air resistance. What is the speed of the rock just before it hits the street? So we're going to throw it up, and then it's going to come back down, and of course here's the street, okay, and I didn't draw windows in the building. Oh, Lord, that's a horrible window. My bad. I didn't draw windows. Okay, you can draw windows, and you can put a door over here if you want to. Okay. All right, windows. Now, so the rock comes all the way back down, and just right, I mean like a nanosecond before it hits the street. We want to know what? We want to know what is its speed of the rock just before it hits the street. So we want to know the final velocity in the y direction. We're looking for y final, right? Vy final. Okay, so let's look at some things that we have. We know, what else do we know? Well, we know the initial velocity. We know the distance that it falls. The building is 30 meters, 30.0 meters. And you can call that h, or you can call that y. You can call that the height of the building, or y. We know that. Okay. What else do we know? Do we know the acceleration? Well, what is the acceleration, y'all? Well, we don't know, Mr. Shields. Well, guys, it's under free fall. It's falling. So it has to be negative g, which would be negative 9.8 meters per second squared. That's going to be the acceleration. So the acceleration is equal to negative g, which is negative 9.8 meters per second squared. So yes, we do know that. Okay, we do know it. Okay, guys, well now here again, we want to know the final velocity just before it hits the ground. Question mark. Well, let's look at our variables. Well, let's see, we've got a displacement. Even though it's in the y, y'all, it's still displacement. Our displacement is 30 meters. You could actually call that delta y if you wanted to. And it all depends on which way you want to go. Since we're starting at the top of the building, let that be 0 and let this be 30. And by the way, we're going down. We're going down. Well, let's think about that. We'll think about that here in a minute. We're going down. And we want to find the what? We want to find the final velocity. Well, I don't have an equation for that. Well, I beg your pardon. I beg your pardon. All right, now, I told you this in class. Just because I didn't necessarily give you a set of X or Y kinematics, listen, guys. The kinematics for X are exactly the same for Y with one exception. One exception. We change the acceleration to gravity and we put a negative in there. Okay? We put a negative in there. So you can do one of two things. You can put negative g, or you can put acceleration and put the negative value of acceleration. In other words, this. So what equation are we going to do? Well, which one fits? Well, we've got an initial velocity. We're looking for final. We have a displacement, even though it's y, x, doesn't matter. So we can use this same equation again. And by the way, this is one that's very useful. Okay? And we're in the y direction. And watch, I'm going to do this. I'm going to go ahead and say plus 2a. Okay, and we can say, we'll just say delta y. Or let me do this. No, let me do this. I'm going to say, I'm going to say, since we're doing y, minus 2g delta y. Okay? All right, now watch this. Okay. We have our initial velocity. We have our final velocity. Now watch. Watch this. Let's solve for final velocity. So final velocity in the y direction, Vy final, is equal to, well, let's solve for that. We're going to take the square root of both sides. And so that's going, and by the way, that's squared. And so this is going to be Vy initial minus 2g delta y. Correct? Okay, now let's just plug everything in. So Vy final is equal to the square root of, and that was squared. So the initial is what? 22 meters per second, and that's squared. Now watch very closely. Minus 2 times, now I'm not going to put a negative in, I've already got the negative 9.8 meters per second squared. But now, whoa, wait a minute, let's look at our delta y. What is it going to be? What is our delta y going to be? Well, guys, look, it has to be negative 30. Because you start out right here, this is 0. Up is positive, down is negative. See, look, guys, if you draw your Cartesian coordinates right there with the top of the roof, because that's where you started. See right there? Well, the origin's right there, 0. 0 is right here at the top of the roof. So that means down this way has to be negative. So that means down this way has to be negative. So it has to be a negative 30 meters. All right, now, when you do all the math, you say, well, wait a minute, what about the initial velocity? Well, look, guys, if the initial velocity right here is 22 meters per second going upward, guess what it is coming down? It's a negative 22 meters per second going downward, but when you square a negative, it becomes positive, right? When you square a negative, it becomes positive. Okay? Yeah. So when you do the math, what do we get? We get 32.7 meters per second, right? Now, when you multiply negative times a negative, it's positive. Well, you can't take square root of a negative under a radical, so it has to be positive. Well, you're right. In a sense, you are right. Mathematically, you are. But it works out to be positive, because when you take that, if this is negative, which it really is negative, because once it gets back here to the origin, it's going down, so that means the initial velocity becomes negative. Okay? All right? Because remember, symmetry, okay? You've got symmetry. If it starts out at positive 22, coming down at the same point, it's negative 22. All right, now watch, and because gravity's constant, So you get 32.7 meters per second. But now hang on a minute. That is right here just before it hits the street. Just before it hits the street. And notice that just before it hits the street is under my starting point. Well, y'all, I drew my y and my x over here. Going up is positive y, going down is negative. So that means the velocity has to be, the final velocity has to be 32.7 meters per second. It has to be. And by the way, this is 32a. It has to be negative 32.7 meters per second because we started at 0, you're under 0. You're beneath 0. You're going down in the y direction, and going down from the origin in the y direction is negative. Now, to confirm this, let's look at part 2. Part 2, how much time elapses from when the rock is thrown up until it hits the street? Okay. Well, now, how in the world are we going to find that, Mr. Shields? Well, okay, well, let's just look at it. Well, we know now the final velocity. We know that. We know gravity, right? We know what that is. Okay. We now need, so part B, we want to know how long, what is the time interval it takes to go up and come back down and hit the street. Okay. Well, how do we find that? Well, go back. Now, remember, y'all, acceleration is constant because it's gravity. Don't forget, y'all, that's constant. I didn't write that down, but you need to know that. You already need to know that. We've talked about that in lecture and class, that gravity is constant. I've said it a million times. It's constant. All right, now watch. Okay. Well, what kinematic of those 4 kinematics that you were given in class, and I told you what page number they were in your text, does it have initial velocity, final velocity, acceleration, and time? Well, this one right here, final velocity, and again, y'all, it's the same. Final velocity in the y is equal to the initial velocity plus AT. Now, I know you say, well, in the y direction, it's this velocity, and that's for x, and that's x. Okay, well, look at it in the y. So final velocity, y final, is equal to y initial minus gt. Now, look, if you use that equation, remember, you don't come in here and put another negative in for gravity. You don't do that. Okay? All right, now let me ask you something else. How do I know that my initial velocity is negative? Okay, solve this equation for t. All right, watch. If you solve it for t, you get Vy final minus Vy initial divided by negative g. Now remember, you don't put negative. It's negative, it's already negative. So I don't say negative times negative 9.8. You don't do that. It's already negative. So now let's substitute everything in. Well, what was my final velocity? Well, we found it to be negative 32.7 meters per second. And what did we find well, it has to be negative because my math does not lie to me. Negative 22 meters. You don't go negative, okay? You don't do that. Okay, you don't do that. All right, we've already got the negative in the equation. The equation, the math tells us that it's negative. It has to be meters per second divided by, I love it when the math works out, negative 9.8 meters per second squared. You can't have a negative time interval, guys. So all the negatives cancel. When you add up negatives, you get negative, and then divide by negative, you get a positive. And so we get a time interval of 5.58 seconds. Isn't that beautiful? When all the math worked itself out. That's why you need to solve for the equation first, always. And then plug your math in. And so we get an answer of 5.58 seconds. Okay? Oh, that's beautiful. Okay, I hope this helps and makes sense.